Hey everyone, Jamie Batts, your instructor for Bio 221. We're going into the second part of Chapter 25, which is all about metabolism. And I'll probably end up breaking this section down into a few videos because it gets a little intense. First, I want to address the term metabolism. The majority of people use the term wrong. You'll say, oh, I'm getting older, my metabolism isn't what it used to be, I used to be able to eat whatever I want, not gain a pound, blah, 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 right? That is the improper use of the word metabolism. Metabolism is the sum of all of the reactions in your body. So from digesting the food, breaking it down into its small parts, and then reassembling those parts into what you need, all of that is metabolism. So it's not just how quickly you lose weight, or how quickly you use the energy from the food that you brought in. That's part of it, but not all of it. So make sure that you understand what metabolism is. Metabolism is the sum of the anabolic reactions, which are the building reactions, and the catabolic reactions, which are the breaking reactions, like digestion, for example. So those two things, anabolism and catabolism, equal your metabolism. So let's talk about it in a little bit more details. It all comes back to ATP and the use of ATP in your body, and this is my favorite diagram ever to draw. Anytime I teach biochemistry, metabolism, this drawing just it all makes sense. And I probably did this for you, I don't know, at another time, but let's talk about it. So it all surrounds around ATP, because ATP is our energy molecule, and ATP is the energy currency for any cell in the body. So whether you're a brain cell, a cardiac cell, a skin cell, a digestive system cell, it doesn't matter, you're going to use ATP for energy. And ATP breaks down into ADP plus P when it's used, and then it's reformed into ATP for energy storage purposes. So when ATP is converted into ADP, energy is released. This is energy to do something. Right? This is the do something is what it says. This is the energy to blink, to breathe, to pump that sodium potassium pump, right? Active transport, all of that stuff at the cellular level is using ATP and turning it into ADP plus P. Now ADP plus P is going to be reformed into ATP when energy is captured. And you might say, well, how is energy captured? Energy is captured from the breakdown of biomolecules. In other words, the breakdown of food. The breakdown of those organic nutrients that you put into your bodies. The sugars, the proteins, the lipids, when those are broken down, you're going to take the energy from those foods, put it into ADP to make ATP. That's what this energy cycle is all about. So we're going to take a look at these kind of, and that's pretty much the drawing there on page 922. I just think it's a really important diagram to understand and get a real grasp on. So if you, I'm just looking at my hair, looks crazy. Sorry, I took it out of a ponytail. So, you know, in other words, if you're thinking that, you know, you're looking at this diagram and you don't understand it, I always suggest redrawing it and trying to paraphrase or summarize in your own words. And that's why I make it my own by recreating that diagram as I did. So let's talk about carbohydrate metabolism, which is the first guy to tackle, as you might say. Carbohydrate metabolism is going to help us understand the lipid and the protein metabolism. So it almost makes sense that we start there first. And I have my eraser stock that I use. So let's talk about how these sugars are broken down. Well, we talked in the digestion chapter that carbohydrates come in, right? They're broken down by salivary amylase, and then they go into the stomach. Nothing really happens to them there. In the duodenum, then you have the pancreatic amylase, which continues the digestion, and then all of those brush border enzymes like the lactase and the sucrase, right? All of those little enzymes that are within the brush border of the small intestine are going to continue that digestion even more. And then we talked about the co-transport of glucose and sodium into the cells. So that into the intestinal cells, right? And so that glucose comes into the intestinal cells, and then it goes out of the intestinal cells into the blood. And then it can go to the liver or to wherever it needs to go in the body. So let's follow that glucose molecule that was just absorbed, and let's say that it goes up to your brain. Alright? So that glucose molecule that was just broken down from some starch or something that you ate went into the intestinal cell, out of the intestinal cell into the bloodstream. Then from the bloodstream goes through the hepatic portal system, and it floats all the way through the systemic circuit and ends up in a neuron in your brain. So what happens there? Well, the first thing that happens to glucose when it comes into the cell is a process called glycolysis. And if you just think of the word, or look at the word, it's glycolysis, literally breaking down glucose. Glycolysis, glycolysis is how it's pronounced. And I just want to make sure I'm including everything from my little notes that I have. Glycolysis has several key players. There's some things that go into glycolysis, and then there's an output. There's things that leave glycolysis. So let's look at this word, and I'm going to make a graphic organizer for it. So going into glycolysis is glucose. As soon as glucose comes into the cell, this process starts. So this glucose, of course, is coming from the food that you ate, broke down, and absorbed from your intestines. It floated around your blood and went to its destination. It also uses enzymes. So these enzymes are actually floating around in the cytosol of the cell. These enzymes like G3P and hexokinase. These are important these are important glycolytic enzymes that are floating in the cytosol. So those two enzymes plus a glucose molecule. What else do we need? Oh, we need inorganic phosphate, PO4, and we need ADP. Right, so this is the ADP plus P, right, the inorganic phosphate and the ADP. That's the whole idea. So what do we get out of glycolysis? Oh, actually, in order for glycolysis to occur, it's actually an energy-using reaction. So ATP actually has to go into it also. So not only do you have ADP and inorganic phosphate, you also have ATP, 2 ATP to be exact. 2 ATP going in. So it's using energy. It's going to yield 2 ATP as well. So it actually makes 4 ATP total. But because it uses 2 ATP, it's only yielding 2. Does that make sense? It's creating 4, but it's using 2, so it's only a net of 2. It's also going to yield 2 NADH molecules. NADH is a coenzyme that's going to play a role later on. It's kind of like a placeholder. It's also going to yield 2 pyruvate molecules. 2 pyruvate molecules. Oh, we also need NAD. And the NAD, as you can imagine, is going to be used to make the NADH. So if we just look at this graphic organizer here for a minute, you can kind of see all of these players put into place. The inorganic phosphate and ADP are going to be used, along with this ATP, to create the net of 4 ATP over here. Our glucose on the whole is being converted from a 6-carbon molecule to 2 3-carbon molecules. The enzymes that do this, well, there's a bunch of enzymes, but these are the key players here, G3P and hexokinase, and we see that NAD is converted into NADH. So glucose is being converted into pyruvate, NAD is being converted into NADH, ADP rather, is being converted into ATP, and here are our enzymes. This is kind of the major players of glycolysis. So, after glycolysis, there is a kind of half step that takes place, and it is a trying to think how I want to segue into this. This half step is basically taking our pyruvate and converting it into, let's see if I have it drawn out anywhere. Oops. Taking our pyruvate and it's converted into something called acetyl-CoA. So our yeah, I do want to draw. I was just evaluating whether or not I wanted to get into this in this video or not, but we're only at 10 minutes. So, alright. So, if we, again, big picture here, we're breaking down carbohydrates. This is all about carbohydrate metabolism. So, our pyruvates, which we got out of glycolysis, are 3-carbon molecules. Glucose is a 6-carbon, right? C6H12O6. So, we have pyruvate is just a 3-carbon. Well, pyruvate interacts with something called coenzyme A. CoA. It's an enzyme, right? We write the enzymes over the arrow. It's just a nomenclature. And what's going to happen is we're going to give off a carbon dioxide. So pyruvate, which is a 3-carbon compound, is now losing a carbon in the form of carbon dioxide. So we're down to 2 carbons. We're also going to take a hydrogen away from pyruvate and create NADH, NAD, which is just kind of floating around there from the mitochondria, just like it was before in glycolysis, is going to come and get a hydrogen added to it. And then acetyl acetyl-CoA, this is like not going to fit here, acetyl-CoA is the, actually I should do it like this, sorry. Is our final product. Acetyl-CoA is our final product. So pyruvate is then converted into a 2-carbon molecule, CC, 2 carbons there. So pyruvate loses the carbon dioxide and is now converted into acetyl-CoA as a 2-carbon molecule. So with that, our now 2-carbon molecule, acetyl-CoA, I'm just going to rewrite it over here, acetyl-CoA, joins up with a molecule called oxaloacetic acid. Oxaloacetic acid is a 4-carbon molecule. Oops, I keep doing that. C, C, C. Oh my goodness. C, C. And this is a 2-carbon molecule. 2 carbon plus 4 carbon. And now we're back to a 6-carbon molecule, which is citric acid. Hence the citric acid cycle. Which is 6 carbons. So, now what is this? Why is this a big deal? Well, because this is actually a cycle. The citric acid, which is created from the joining of acetyl-CoA and oxaloacetic acid, goes through a process now. The citric acid loses 2 carbon dioxide. Those 2 carbon dioxide, so we have a 6-carbon compound losing 2 carbons here. We're down to 4 carbons. Guess what? That's oxaloacetic acid. This oxaloacetic acid joins with another acetyl-CoA that was formed from another pyruvate to undergo the whole process again and again. It's a cycle. So, citric acid, taking away those 2 carbon dioxide, is going to give us that oxaloacetic acid, along with these waste products here, oxaloacetic acid plus 3 NADH and 2 FADH2. Oh, sorry, that's super sloppy. FADH2. So you might say, alright, well, what's the big deal? Well, if you look in your book on page 923, you'll basically see everything that I just drew out for you, but in a little bit more detail. What I drew out for you is in a little more detail. And the reason I drew it out in that level of detail, again, I'm a big picture person. I like to understand what's going on and why it's important. And I think it's important to understand how those carbons change. Because what you're seeing is where that carbon dioxide that we know, you've probably known it since high school, carbon dioxide is what we exhale. You're seeing where that carbon in the carbon dioxide comes from. It comes from the glucose that you're bringing in your body. You bring that glucose in, it gets converted into pyruvate, it gets converted into acetyl-CoA. That acetyl-CoA combines with oxaloacetic acid to make citric acid, and the byproduct, when it's losing those carbons, is carbon dioxide. And so I think it's important to understand that big picture. What else are we creating? We're creating NADH and FADH2. We created some NADH from glycolysis. In the citric acid cycle, we created some more, as well as some FADH2s. Those molecules are called coenzymes, and they're going to play a huge role in the next step of carbohydrate metabolism, which will start on the next video.